Hello, my name is Dr. Mo Shiva. I am a professor of electrical engineering at California State University, Fullerton. The purpose of this video is to do an example using nodal analysis. I will do 3 examples in 3 different videos, this being the first one, with the assumption that you're familiar with basics of nodal analysis and the steps to be taken. To do a quick review of nodal analysis, first step, doing nodal analysis, mesh analysis, or anything else, is, if possible, simplify the circuit. That is always our first step. For nodal analysis, we choose a reference node. It could be assumed to be ground. It doesn't have to, but we treat it as having 0 volts. And simplifications in the solution occur if the reference node is the node to which the greatest number of branches is connected. We assign voltages to non-reference nodes. We apply Kirchhoff's current law to non-reference nodes. Preferred version of Kirchhoff's current law for nodal analysis, I would like summation of currents leaving a node equal to 0. A little bit later, we will see that helps us in avoiding making sign mistakes. For an n-node circuit, nodal analysis results in n-1 equations in n-1 unknowns, unknowns being nodal voltages, and we can solve for those. We never apply Kirchhoff's current law to the reference node. In our first example, the circuit contains only resistors and independent current sources. This is the simplest possible circuit for nodal analysis. In the circuit below, we want to use nodal analysis to find nodal voltages, and the problem says take the bottom node to be the reference node. A few things to do. First, we have to simplify the circuit to see the nodes clearly. So we have a node here, we have a node there. This looks like 2 different nodes, but they are not. There's a short circuit there. And what we see is all of these points at the bottom of the circuit are shorted to each other. So basically, that is one node. For Kirchhoff's current law, easiest version to get a feeling for is summation of currents coming to a node is equal to algebraic summation of currents leaving the node. In other words, for the little figure that we see here, I1 equal to I2 plus I3. I1 gets to the node, splits into I2 and I3. However, the best version to use for nodal analysis is summation of all currents leaving the node equal to 0. So right now, I2 and I3 are leaving the node. If we switch from I1 to negative I1, that current is now leaving the node. So the version that we'd like to use is negative I1 plus I2 plus I3 equal to 0. One more thing, we're using passive conversion for the resistors. So if we have a resistor with resistance R, voltage V, current I should be entering the positive reference of the voltage. And for this, V is equal to Ri. An equation is not as simple as it looks. We're talking about voltage drop across the resistor being equal to resistance times current entering positive reference of the voltage. Then for nodal analysis, we use I equal to V over R. You see a little circuit here. Reference 0 volts is at the bottom. We have nodal voltages V1 and V2 already assigned. And meaning of that is
voltage of node 1 compared to the reference is
plus on the top, minus at the bottom, V1.
voltage of node 2 compared to the reference, positive on the top, negative at the bottom. In other words, voltage drop across the 1 ohm resistor is V2.
So if you are interested in the current going down here, using the passive conventions that we have on the left, that current is V1 over 2. The current going down the right branch from V2 to reference is V2 over 1. What if we want the current going, let's say for the sake of argument, from left to right on the top branch? That should be the voltage here with plus on the left, minus on the right. And that voltage is, look at the plus side, we have V1, and on the minus side, we have V2. So it's V1 minus V2, as simple as that. So we would get V1 minus V2 over 3. V1 minus V2 is kind of obvious. It's simply Kirchhoff's voltage law. Voltage drop from node 1 to node 2 is independent of the path. So if we move from top left node to top right node through another path, we should have the same voltage. So move down, we see positive. So write it as positive V1. Then move up. On the right hand side, we see the negative sign, so negative V2.
So V1 minus V2 is the voltage to be used.
Let's simplify the circuit to see the nodes clearly. So that is our simplified circuit. V1, V2, and V3 are assigned. Do not bother at this point trying to figure out direction of the currents and whatnot. 16 amps is coming to the node. How is it splitting? Where are these currents going? That is just a waste of time. Do it by simply applying Kirchhoff's current law as summation of currents leaving non-reference nodes equal to 0. So looking at the figure and node 1, we want to add these three currents together and put the sum equal to 0. So node 1, we have V1 over 1 over 11 plus through the 1/3 ohm, voltage across it is V1 minus V2. Divide that by 1/3. And on the top, voltage with positive on the left, negative on the right is V1 minus V3. And divide that by 1/4. And that sum should be equal to 0. For node 2, look at the three currents. Go around, make sure we don't skip any branches. So we have V2 minus V1 over 1/3. Next component, current going straight down, is V2 over 1. And to the right, we have V2 minus V3 divided by 1/5, and that's equal to 0. For node 3, through the 1/5 ohm resistor, we need positive on the right, negative on the left for the voltage. So we have V3 minus V2 over 1/5. We add to that, through the 1 ohm resistor on the top, we need the current going left. So voltage is V3 minus V1 over 1/4. Going straight down, we have V3 over 1. And current leaving the node through the current source is minus 16 equal to 0. If we use the currents leaving the node equal to 0, we can quickly check for a sign mistake. Through the resistors, for node 1, we should always have positive V1 or positive V1 minus something. So quickly check for a sign mistake. For node 2, we should have V2 first. So positive V2, positive V2, positive V2. So if we had for the last time V3 minus V2, we could quickly notice that we have a mistake there. A reference 0 volts, everything is compared to that. 3 equations and 3 unknowns. Let's simplify these. So we end up getting 18V1 minus 3V2 minus 4V3 equal to 0. Let's call this equation 1. Node 2, we get negative 3V1 plus 9V2 minus 5V3 equal to 0. Call that equation 2. And the last equation is negative 4V1 minus 5V2 plus 10V3 equal to 16. That's our third equation. Now, let's eliminate V1 through these equations. We have 18 in the first equation, negative 3 in the second equation. So let's multiply the second equation by 6 to change that negative 3 to 18. So get equation 1 and add to it 6 times both sides of equation 2. That gives us 51V2 minus 34V3 equal to 0. Call this equation 4. And let's change that negative 4 to 18 and add that equation to the first equation. So we need to multiply 4 by 4.5. That gives us negative 18. So take equation 1 and add to it 4.5 times equation 3. we get negative 25.5 V2 plus 41 V3 equal to 72. All right, now let's change that negative 25.5 to 51 so we can eliminate V2 in these two equations. So let's take that equation and simply multiply it by 2. We have negative 51 V2 plus 82 V3 equal to 144. Now, if we add equation 4 to this equation, we eliminate V2 and we get V3 times 48 equal to 144. So V3 is 144 over 48 equal to 3 volts. Using equation 4, V2 is equal to 34 V3 divided by 51 gives us 2 volts. Then let's go back to equation 1, which is relating V1 to V2 and V3. So equation 1 is resulting in V1. Find V1 from equation 1. We have 3V2 plus 4V3 divided by 18.
Substitute values of V2 and V3 and we will end up with V1 equal to 1 volt. Looking at equations 1, 2, and 3, we have 3 equations and 3 unknowns. And obviously, another method for solving that system of equations is using Cramer's rule and determinants.
So sometimes elimination of variables is easier. If you want to use Cramer's rule, V1 would be the denominator is determinant of the coefficients of the left-hand side of the 3 equations that we have there. So denominator is 18, negative 3, negative 4, negative 3, 9, negative 5, negative 4, negative 5, 10. And since we are looking for V1, we change the first column of that matrix with the constants on the right hand side of equations 1, 2, and 3. So here we get 0, 0, 6. Rest of the numbers stay the same. Negative 3, 9, negative 5, negative 4, negative 5, 10. So we have replaced the first column, it's V1, so replace the first column of the denominator with constants on the right hand side of the equation. And basically, I'm assuming you know how to solve the determinant. We will find 816 over 816 equal to 1 volt, which is the correct answer. Some books emphasize the form of this matrix. We see we have positive numbers on the main diagonal, negative numbers off diagonal, and also matrix is symmetric. Those are the properties that we see because in this circuit we only have current sources and resistors. With current sources and resistors or conductors, that will happen, but if we add dependent sources or other types of elements or voltage sources, we will lose that. So it's not really that important. At this point, anything else is easy to find. So we have V1 equal to 1, V2 equal to 2, and V3 equal to 3 volts. So whatever the unknown of the problem is, we can find it at this point. So if you are interested in the current going in that direction, we need positive on the right, negative on the left. That's the voltage that we want to use. So this current is V3 minus V1 over 1/4. Gives us 8 amps. If you are interested in the current going to the right from V1 on the top, then this should enter the positive. So we want positive on the left, negative on the right. So that would be V3 negative and V1 positive. We're going from node 1 to node 3, V1 minus V3 over 1/4. It gives us negative 8 amps, opposite direction. If you're interested in current going down here, that would be V1 divided by 1 over 11, 11 amps. So currents, powers, anything the unknown of the problem is straightforward to find after we have the nodal voltages. For power, we use VI, and if you're looking at an element with voltage V and current I, this equation means power absorbed by the element, we're talking about absorbed power, is equal to voltage times current entering positive reference of the voltage. If you want to find power for any of the resistors, it's easier to use P equal to RI square. One more thing about this problem. Let me quickly redraw the circuit. The nodal voltages that we calculate, they are all with respect to the reference node. In other words, if we look at the same circuit, and this time we take, let's say, the node on the top right to be the reference node, then we are saying here we have 0 volts. Solving the same problem, we find the voltage of that node to be -2, voltage of this node to be -1, and voltage of the bottom node to be -3 volts. So basically our reference, which was 0 volts before, results in 1, 2, and 3 for V1, V2, and V3. Now we are taking our new top right node to be the reference. So if you compare these two, we are subtracting 3 volts from V3. And everything is calculated compared to that. So to get the answers from the top figure, just subtract 3 volts from the other nodal voltages and we have the answers. This ends our first example. I will do 2 more examples. As I said, this is example 1 out of 3. And we will do nodal analysis again, except I will add new elements to the problem.